Hi, everyone. As he just mentioned, my name is Kevin Klues, and I'm a distinguished engineer at NVIDIA. I assume if you're at this conference, you probably know what containers are. But just to frame the conversation a bit about what I mean by containers, because everyone has a different meaning for when they say containers, what they actually think in their head. And for the purpose of this talk, we're going to be thinking of containers as a packaging mechanism for applications, where you can bundle dependencies together with an application. You can have consistent and reproducible deployments from this. That are more lightweight and have faster startup times than with VMs, and they provide logical isolation from other applications at the OS level rather than the VM later. So kind of like what you would see here on the left, if you're picturing how this would run on top of something like GPU hardware. And if any of you have interacted with a component called NVIDIA Docker, this is how it kind of works under the hood. We have some way to have a container that runs on top of Linux where you've got the GPU hardware underneath, and we find a way to inject the GPUs into those containers so that you can run your GPU workloads on them. I assume most of you are also familiar with Kubernetes. I'm not going to explain what Kubernetes is, but one thing I want to point out, I'm a maintainer of the kubelet within Kubernetes, and we're currently in the process of trying to make Kubernetes the go-to platform for running AI and ML workloads in the cloud. So until today, there's been different goals that Kubernetes has had over time, and now it's at this transition point where we're trying to make it this platform. And some of the stuff I'm going to talk about today is what we're doing to help make that possible. So let me just kick off with talking about what some of the challenges are with supporting GPUs and containers today. So before containers, it was actually easy. You could buy some GPUs, you could install them on your box, you could install the NVIDIA driver inside the Linux kernel. You could then install some advanced toolkit libraries up in user space. You could link a GPU accelerated application against these libraries, and then you run your application, and everything just works, in quotes. So what about containers? You'd think the process should be similar, right? You buy some GPUs, you install them on your box, you install the NVIDIA driver. This part still makes sense. And you'd want to be able to build a container image, bundle those NVIDIA driver libraries, bundle the advanced toolkit libraries, and also bundle your GPU accelerated application inside of this, and then run your container. It seems straightforward. But the problem is that this will actually only work if the kernel and user space portions of the driver match exactly. So in the example I'm showing here, I'm saying that the NVIDIA driver libraries are at version 1, and the NVIDIA kernel driver is also at version 1. But it won't work if they don't. So if you happen to bundle even a slightly different driver version all the way down to the patch release inside your container, it won't work on a driver that has just a slight minor or even patch release version skew from what you have inside your user space libraries. So our solution to this over time has been to inject the host driver libraries at runtime instead of bundling them in the container. So again, if you've ever interacted through NVIDIA Docker or the functionality that we've built into Kubernetes, this is all going on under the hood. We're doing this runtime injection of the user space NVIDIA libraries into your container so that you don't have to bundle them, and so that can be portable across different machines with different kernel driver versions for the GPUs. And then we also, obviously map the GPUs into the container as well. And the component we use to do this is called the NVIDIA Container Toolkit. So behind the scenes, if you're doing an NVIDIA Docker run, you're pointing it at the NVIDIA runtime like you see in the example. You're telling it you want access to GPUs 0 and 1. It's the NVIDIA Container Toolkit component that's sitting behind the scenes doing all the work to make this injection happen for you so that you don't have to think about it. And it's also what's going on behind the scenes if you happen to use Kubernetes and you request GPUs similar to what we have in this pod spec that you see here. So you say nvidia.com/GPU2, and as long as your pod can find its way to a node that has GPUs on it, you'll get 2 GPUs injected into it using the NVIDIA Container Toolkit. And so the question is kind of, how do we do this? What's the technology behind the scenes that allows us to do this injection? And the NVIDIA Container Toolkit has gone through many iterations over time. We first implemented it all the way back in 2015 when containers were first starting to kind of gain traction in the community. And it's taken a lot of different forms over time. And the one that we're kind of, have consolidated around today is this new interface, CDI interface that we've been pushing together with Intel as a CNCF-sponsored project under the tag runtime. And it aims to standardize the way in which complex devices are exposed in containers. And I say this with a capital D because a device isn't just a device node, like a Linux device node that you inject into your container. There's a lot more that you want to come along with that potentially. And I'll talk about that in a second. And as part of this, there's a declarative specification of what it what is required in order to use one of these devices. So it's the device nodes, it's a set of library mounts, it's a set of potential sockets that you need injected into the container, and you can specify all of this in this CDI spec, and then when a runtime picks that up, it knows how to inject your named device with all of those things attached to it. And yeah, it's an abstract concept that lists all these things: device nodes, mounts, environment variables, and hooks. At the end of the day, vendors are responsible for producing CDI specs that define their devices. So NVIDIA can produce this, Intel can produce this. Any vendor that wants to make use of CDI can produce these CDI specs, and runtimes that support CDI can pick those up and make those devices available to the containers. Where a CDI device itself is uniquely identified by what we call its fully qualified CDI device name. And so that's a vendor class name construction like you see here, where you could have at the end, you'd have vendor.com device equals your named device. And for the case of NVIDIA GPUs, we tend to construct them like this. And so the example at the bottom here, where you see docker run -- device NVIDIA.com/GPU0, this is actually something you can do as of Docker 25, I think it is, whatever the most recent release of Docker is. They have support for CDI now, so that you can use this syntax to get access to GPUs behind the scenes. And you don't have to rely on the NVIDIA Container Toolkit anymore. It's all built directly into Docker and its use of the CDI specs that we as the NVIDIA vendor will generate. So what does one of these CDI specs look like? So on the left, you can see, this happens to be using CDI version 050. I think we're up to 070 or something like that now, where you give it a kind. In this case, it's NVIDIA.com GPU. You have a list of devices. I'm only showing one here right now. I've given it the name 0. I say what device nodes I need to be injected if you ever reference this named device of NVIDIA.com/GPU0. And those devices are NVIDIA 0 and NVIDIA Control under the dev file system. There's also a bunch of mounts that need to be injected. So I mentioned that, because of these challenges we have with supporting GPUs and containers, you have to inject the user space libraries at runtime into the container, and this mount section lets you specify what those libraries actually are that you need injected. And there's also a set of hooks that you can run, and the most common one that people tend to run is this update LD cache hook, which allows you to, as your container starts, make sure that all of these libraries you just injected are part of the library path, so you don't have to set up some custom LD library path or run LD config yourself behind the scenes. It'll do that for you before the container comes online. And where does this fit in? So as I mentioned before, there's a separation of generation from consumption. So nowadays, we have a tool that we provide called NVIDIA CTK, which can inspect any GPU system, figure out what devices are there, and it will create one of these NVIDIA.com GPU, or create one of these CDI specifications with all of your NVIDIA.com GPUs specified in it, so that you put that on the file system somewhere, and then after the fact, a runtime can come along and pick that up and eventually, consume that spec in order to give the container process access to the GPUs once it starts up. And we also have support for this. That's kind of an offline generation cycle. And we also have support for this for dynamic generation in the GPU device plugin and in the future in DRA plugins that we have inside Kubernetes. If these acronyms don't mean much to you yet, I'll be talking about them later on in the talk. And once you've dynamically generated these specs, then the consumption piece can kick in again, and it can pick it up and make sure the GPUs are available inside your Kubernetes cluster the same way they are inside a standalone container runtime. So why CDI? Why are we pushing this as the model to adopt going forward? Well, one of the main reasons is that vendors, be it NVIDIA or Intel, can define what access to a device means. And vendors don't need to integrate with any specific container engine. So in the past, we've had this kind of crazy architecture to make sure that we worked with all these different container engines in different ways. And now we just offload that into the spec, assume that the container runtimes are going to be able to pick up this spec and make use of it. And so as long as the container runtime opts in to consume the CDI device and use the spec and use it to inject devices, our work as a vendor is done. And it allows for uniform user experience across different vendors and tools. And so the one that we've kind of consolidated on, at least in terms of Docker, Podman, Singularity, I think there was actually support added to Alexi just last week or 2 weeks ago, is with this -- device flag, like you tend to be used to in a lot of these containers. And so the -- device is now overloaded to accept CDI devices in addition to standard Linux device nodes. Okay, so that's kind of what we do in containers and how we enable GPU support inside containers today. So what does it look like inside Kubernetes? And how do we get GPU support working inside Kubernetes? Well, there's a set of two types of components that you need to have deployed in your cluster in order to use GPUs in Kubernetes. There's a set of host-level components, which are the NVIDIA Container Toolkit and the actual GPU driver itself installed in the kernel with the user space libraries available. And there's also a set of Kubernetes-specific components, the most important of which is the K8s device plugin, which knows how to enumerate the set of GPUs on the system, make them available, advertise them to Kubernetes so that your pod spec can eventually reference them and get them injected into the container when it starts running. And we also provide a component called the GPU operator, which bundles all these things together and kind of automates that process for you. So in theory, you could come along, you could deploy all these components yourself, you could manage all of that across your infrastructure, but if you make use of the GPU operator, you just deploy the GPU operator in your Kubernetes cluster. It's able to auto-detect what nodes have GPUs on them, get the entire software stack they're running, start advertising the GPUs, and now your workloads can start running without too much extra effort on the side of the system administrator. And so as I showed before, this is kind of what it looks like to request access to GPUs today. You have a pod spec, you have a resource section in your container, you set limits for this extended resource of type nvidia.com/GPU, and you say how many you want. And magic behind the scenes happens, and eventually your pod gets access to the GPUs, landing on a node that has those GPUs available. If you want a specific type of GPU, the only way to do that, at least currently, is via node selector. So this kind of assumes that all the GPUs on a given node are identical, and you have a set of labels declaring what those GPUs are and what they look like, and what their product name is, what CUDA runtime version they're running, what CUDA driver version they're running. And if you use a node selector, you can be sure you're going to land on a node that has that type of GPU, so that the nvidia.com/GPU resource type that you're referencing actually refers to one of these GPU types and not some other one. We also have the ability for you to request a fraction of a GPU. So there was a technology that came out back in 2020 called MIG, which is short for multi-instance GPU, and it lets you at the hardware level divide up a set of GPUs into a set of kind of smaller mini GPUs, and we expose them in Kubernetes using a different extended resource type, where the name of the MIG device that you're trying to reference is encoded in the resource type. So in this example, I'm showing how you get access to a single MIG 1G 5GB device, where 1G kind of encodes the proportion of compute resources that you have available on the device, and 5GB says how much memory that device that you're asking for has. We also have the ability for you to time slice access to full GPUs. So this is it's a couple-year-old feature that we have. Not everyone's necessarily available or aware of it, but inside your config for the device plugin, you can specify a number of replicas that you want to have for a given resource type, in this case, nvidia.com/GPU, and it basically describes how much you want to oversubscribe that resource on a given node in the cluster. And so the example I'm showing here basically says that if you had one GPU available on this node, it's going to actually advertise 3 GPUs to Kubernetes, and the CUDA runtime behind the scenes will make sure and time slice the different CUDA processes that get launched on that node behind the scenes. So you as the end user don't need to think about the fact that you're being shared with some other GPU, other than you need to kind of be aware with this strategy how much memory you're allocating, because there's no memory limits enforced between different CUDA contexts that are asking for access to a GPU using time slicing. And this extends to MIG devices as well. It's not just for full GPUs. So if you want to ask for this small hardware partition on the GPU and then time slice CUDA context on top of that, you can do that. The final kind of sharing mechanism that we have, at least available in Kubernetes today, is this concept of space partitioning, which is enabled through an abstraction in CUDA called MPS. And if you configure your device plugin to say that you want sharing being done via MPS, and you tell it how many replicas you want, it'll basically divide your GPU into equal-sized chunks in space rather than in time. And with space partitioning, you actually do get guarantees on the limit of memory that each of the different CUDA contexts are able to consume, and so you don't interfere with other CUDA contexts that are trying to run something in parallel on the same GPU. But with all of that, There's a bunch of limitations. I'm just going to list a few of them here. One of the main ones is that there's no support for having more than one GPU type per node. So I mentioned you can use node selectors to get access to a GPU, but because that's a property of the node, not a property of the GPU, there's no way to have multiple GPUs per node because there's no way to kind of jump in and say which GPU type you want beyond using a node label. There's also no support for providing complex constraints when requesting a GPU. So, the only knob you really have is a number. It says how many do I want, but you can't put much more complex constraints on it than that. There's also no control over how oversubscribed GPUs are shared between jobs. So we allow you to put something like, NVIDIA.com/GPU.shared to share in time slicing or in space partitioning mode, but you don't have any control over which exact jobs share access to which physical GPU behind the scenes, right? The Kubernetes scheduler and the kubelet in particular does all of that allocation for you without you as an end user or even a sysadmin being able to control what it's doing behind the scenes. There's also no ability to dynamically provision MIG devices based on incoming requests. So I mentioned that you can partition these GPUs into these smaller MIG devices, and once you have them, you can request access to them. But that's something the sysadmin has to do a priori. You can't just put a pod request in for a specific MIG device and expect the system to kind of come along after the fact, configure that MIG device, make it available to you, and inject it into your container. It's just not sophisticated enough to do that. And there's also no ability to align different devices, such as GPUs and NICs, on something like the same PCIe root complex. There's just no built-in support for doing things like that. And the list goes on. And so the answer to this is this new abstraction that we've started building into Kubernetes called Dynamic Resource Allocation. And it aims to solve all of these problems and more. Where dynamic resource allocation itself is a new way of requesting resources that have been available in Kubernetes as an alpha feature since 1.26. So it's been a couple of years now, and it's still in an alpha phase even today, but we're hoping that it will graduate to beta as soon as 1.32, which, for those of you familiar with the release cycle of Kubernetes, will come out in December. And it basically provides an alternative to the count-based interface of, for example, NVIDIA.com/GPU2. And it provides a much richer API for requesting and configuring resources, and it's inspired by the persistent volumes API. So if you're used to and comfortable with using the persistent volume API in Kubernetes, DRA will look very similar. And it uses CDI under the hood to do its device injection. So that's kind of the link between what I was talking about with CDI before and this new feature coming up with DRA. It uses that behind the scenes. And some of the key concepts in it, which are similar to the persistent volume API, is this notion of a device class and a resource claim. At the lowest level, inside a given DRA resource driver. So in order to enable this, the same way we have the K8s device plugin that can enumerate resources so that pods can say, oh, I want NVIDIA.com/GPU2 in their pod spec. In the DRA world, there's still a driver that needs to run on any individual node. It's a daemon set running on individual Kubernetes nodes. But instead of advertising just a flat set of devices that are encoded in some opaque string, there's a complex object now that these daemon sets will advertise. So any individual GPU node in the cluster will advertise a resource slice. This is an in-tree Kubernetes object. It's not something specific to GPUs. You say what driver this is associated with. In this case, it's the gpu.nvidia.com driver. And then you list out a bunch of devices and a bunch of properties that are associated with them. So in this example here, I'm showing a single device called GPU0. And some of the more interesting properties that it has are that this specific GPU is a GH200 GPU with 90 gigabytes of memory. And then down below, you can see that we declare that it has a capacity for memory of 96 gigabytes. And there's more attributes that we obviously attach to these, but I couldn't all fit on a single slide. And then with that, as part of our installation of the driver, we've got Helm charts that wrap all this stuff. We also did install a device class in the cluster, which we give it a name. In this case, we reuse the gpu.nvidia.com name for the class that matches the name of the driver that got installed. And all it does is it defines this cell expression for saying that any resource claim, which I'll show what those are in a second, that references this device class, can pull devices from the gpu.nvidia.com resource driver. And so when that happens, behind the scenes, the schedule will be able to figure out, okay, what resource slices are there, what driver advertises these, and can I hand that out to a container down the road. So from a user's perspective, it kind of looks like this. So if we start at the bottom, we've got a pod that now has a new section in it called resource claims. You point that at some named resource claim. We're calling that shared GPU. And if we jump to the top, this is where we're defining the actual resource claim. It's got that name shared GPU, and all we're doing here is saying that this resource claim is putting in a request for a device using the device class name of gpu.nvidia.com that I just showed on the last slide. And once you do that, this resource claim basically gets instantiated, gets a GPU bound to it, such that when the pod inside its container specs reference this shared GPU, they are now going to get access to that same specific underlying piece of GPU hardware that was bound to this claim. And so it enables you to have more controlled GPU sharing of the GPUs that you want. It's not just left up to the kubelets to hand out these resources however it sees fit. And you can also do this across pods. So it's not limited to within a single pod sharing access to the GPU by its individual containers. You can have this global resource claim. You reference that in 2 different pods, and now the 2 GPUs in those 2 pods are running their logic on top of that same underlying GPU. And all of this is protected within a single namespace in Kubernetes. So, users running jobs in one namespace can't reference the resource claims of users running jobs in a different namespace. It's all, this top-level resource claim type is a namespaced object, not a global cluster object. So this is what a device class looks like. As I mentioned before, we've got device. It's basically just saying that you can select any device governed by the NVIDIA DRA driver for GPUs. We can add some more sophisticated logic to our resource claim to not just say, I want a shared GPU that references this specific device class. I also want to configure it in a certain way when a GPU is bound to it. In the example I'm showing here, I want it to be set up for time slicing with some specific duration, whether that's default, short, medium, or long. This is actually something you can do with NVIDIA SMI on the command line if you happen to be on a bare metal machine with GPUs. And now we push this into the configuration you can put on a GPU when it gets allocated to you within Kubernetes. And we also have the ability for you to set up how you want your MPS space partitioning to be configured on a GPU when you get access to it as well. So it's not limited to time splicing. We also have MPS support for this as well. And so kind of putting that all together with a more complex example, you can imagine if I have a resource claim that, for demonstration purposes, I'm calling it big GPU with aligned NIC. I can put in a request for a GPU that has at least 80 gigabytes of memory. So there's this special syntax for cell expressions that allow us to say, give me a device whose capacity field of memory is greater than or equal to 80 gigabytes. And when this claim gets allocated, the scheduler will make sure to bind this GPU that has these properties to it. But along with that, I also want to get access to a NIC from the rdma.nvidia.com driver that's mapped into this resource class. And I want you specifically to give me a virtual function from a network device that's allocated by this. And then I want to link those 2 things together through a new section in these called constraints, which says that for my GPU and my NIC requests, make sure they both have an attribute called k8.io PCI root that has the same value. And so what it essentially does at the end of the day is it says, okay, give me a GPU, give me a NIC. It's going to find some node that has that, and then it's going to make sure that they're both on the same PCI root complex at the end of the day, so that you get faster communication over the network by having the NIC close to the GPU. With the model that we put together in Kubernetes 130, we actually cover 6 of the 12 use cases that I defined in this kind of long list of what we need from Kubernetes to be able to properly support GPUs inside Kubernetes. I put this document together in the context of DRA. So it kind of assumes you have DRA. How can we use DRA to enable these use cases? And as of 130, we supported basically half of them. You could get controlled GPU sharing. You could have GPU selection by complex constraints. You could get multiple GPU types per node, user-driven time slicing in MPS. And you could also, it's not something I mentioned in this talk, but you could dynamically swap the NVIDIA driver with a VFIO driver if you wanted to launch a virtual machine, for example, instead of just running a container via Kubernetes. But there's a list of other things that weren't yet supported, at least not in this version. in 131, and I said by 131, I guess I forgot to update the slide, but in 131, we added support for 2 more. And by 132, we plan to support all of the use cases that were identified in this document, except for one, which is about application-specific policies for how GPUs are allocated across containers. Once you get down to this lowest level of being very, very application-specific, it's very hard to generalize it in a way that the built-in Kubernetes scheduler can, implement the right logic to do it in a very application-specific way. If you're interested in DRA and learning more about it, here's some previous talks that have been given by myself and others at various KubeCons over the last couple of years, where the main one that I'll highlight is the one I gave in Chicago last fall, which kind of first introduced this and how you can use it to unlock a whole bunch of different features in GPUs that you couldn't do today. And I go into the details, I show some demos, and I really kind of highlight why this is an important thing and why it's such a big deal for the community to start working towards having this. And if you're interested in tracking the latest DRA developments, I have a list of the resources here. So the source of truth for all of this is in the Kubernetes enhancement proposal, written by Patrick Oley from Intel. And we also have a device allocation working group in Kubernetes that meets every other Tuesday. In fact, they're meeting right now. I'm missing it to give this talk. That kind of, the first thing on our charter is to enable DRA, but we'll have different things coming up down the pipeline in the future that's within the scope of the working group. And then I also have an example DRA driver that I've put together for GPUs. So you don't have to have GPU hardware. If you just want to play around with DRA and learn how it works, you can run this on your MacBook. You can run it anywhere. It just creates a set of fake GPUs and shows you how kind of DRA is constructed and how you might put together a driver if you wanted to then adapt that to your own hardware down the road. There's also one that's been put together for networking. And then obviously we have the DRA driver for GPUs, which hasn't actually been updated yet for the new 131 changes, but I plan to have done in the next couple of weeks. So yeah, so please reach out if you have any use cases where you think DRA could help, because we're really pushing this forward in the community, and we want to see it be successful, not just for us, but also for any other vendors that are trying to make their hardware available in Kubernetes. Oops. And that's it. I'll take any questions. Thanks.
Cool. Thank you, Kevin. We do have a little bit of time for questions. So first one would be, what is the performance impact of sharing GPUs?
Yeah, so as I mentioned, there's a couple different strategies for sharing GPUs, and there's a couple different trade-offs for why you might pick one GPU sharing strategy over the other. Obviously, if you're doing time slicing, there's a clear performance impact because you're going to be doing something for a bit of time. You're going to be swapped off, and now another application is going to start running, and you're not going to be doing anything during the time that you're not running. Whereas the space partitioning one, you get to run all the time, but you're limited in how much memory you can ask for. And so, the time slicing one is good for, batch jobs when you have the things you need to run. You don't care when they finish. But you have a limited number of GPUs that you have available to you to run these workloads on. Whereas the space partitioning one is really good for latency-sensitive applications if you know you don't need a huge amount of GPU memory, because they will continue to run in parallel.
Cool. I think so next question is, I think when AI is well developed, there will be no PM management tasks. I think management tasks will be handled by AI, so just software engineer and machine. What do you think about AI development in 10 years?
Yeah. This reminds me actually of a quote that a professor once told me back in grad school was, as a low-level systems engineer, if you do your job right, no one knows you exist. But the minute you do your job wrong, everyone knows you exist, because everything you've just built, relies on that. And I don't think at this lowest level, things are going away. They might be going away at the application level, but the low-level system stuff, I think, in containers, very likely exist in this space. I don't think that's going away anytime soon.
Cool. And the final one, any support limitations for Windows Node?
Yeah, there is no support on Windows, unfortunately. This is all on Linux. Yep.
Yep. Cool. All right. That was the last question. Thanks, Kevin, again.
Yep. Thank you.
Applause, please.